Thank you. Welcome to our lecture. We are just opening the conference, and it's proud for us to be the first speakers today. And we will talk about management engine, and actually this research was performed by three persons. Me, Dmitry Sklyarov, my colleague Maxim Goryachy, and other third colleague, Mark Yermolov, who is not here right now. And during last 2 years, we have published some presentation and papers about management engine and platform security. So if you're interested in management engine research, we strongly recommend you to check all this presentation after this PDF will be available, so you will be able to just to follow the links on the slide. We will talk about some hardware features related to security that available within Intel Management Engine. We will talk about a very important part of security mechanism called security fuses. And we will discuss how Intel engineers make decision about calculating keys that required for operating of management engine, and some things that we consider to be kind of magical, make some fun for us. If you're not familiar with management engine, several words from the very beginning. If you look at picture at left, you could see that Intel Management Engine in the middle of the computer system, it's official documentation from Intel. So it have control almost over any device on your computer. If your computer not older than 10 years, that for sure it have management engine inside it. Story of Intel Management Engine goes back to 2005, so it's more than 10 years of that technology. And starting from year, I believe, 2012, all modern computers that produce it on Intel chipsets are use Intel Management Engine version 11, or starting from this year, version 12. In this speech, we will concentrate on Management Engine 11. And when we talk about privileges and rights that could be used to access some data or some equipment on your computer system, most of you, I believe, knew the classic model user level and kernel level ring 0 and ring 3. And under that, there could be a level that provided by hypervisor, and hypervisor could control everything, include kernel mode, but even from kernel administrative rights, you're unable to control hypervisor. And under the hypervisor, there is system management mode. It's special mode for central processor that could operate on some very important tasks on the computer, and even from hypervisor, you should be not able to control that mode, but from lower mode, you're able to control everything upper. And management engine, it's not a part of central processor, it's separate processor, it's on chipset, microchip, and it could operate on every device. It could have access to any memory, including RAM, general memory of the computer. It could, for example, according to documentation on AMT, Active Management Technology from Intel, using Management Engine and AMT, you're able to remotely turn on the computer, boot it from remote hard drive, so it's just virtualized USB device and virtualized SATA drive, and control it in keyboard, video, mouse mode, and shut down the system, and everything could be performed remotely. So Management Engine provide you and developers of the platform provide a lot of ways to control your system. So it's very interesting object for research, and there are almost no public information from Intel. So you could find very teeny pieces of information on internet, but everything else you need to find by yourself. And during last couple of years, we made a lot of efforts to make our knowledge about it deeper, and now we present next piece of our research. So let's start from a review of security hardware that available inside management engine. Again, management engine, it's not a mode of central processor. It's a separate processor, and it's able to work even when your central processor is not powered. So when you plug your computer in the power outlet, or just when you have notebook with not detachable battery, management engine already works. It's already able to control your computer. And there is some simplified picture. We have many special devices that are required for security and actively used by management engine. This part of random access memory is controlled by management engine. It's not available, not accessible from central processor. It's internal memory. It's a little amount of it, about 2 megabytes, but it's needed for running management engine even when your main memory, several gigabytes of memory, is not powered on, not available. So we have security fuses device. We have several devices that handle some cryptographic primitives. We have secure key storage for storing the keys that use it inside memory, inside the management engine. And we have external flash device that holds some data and some code and so on. And let's start from flash controller. Flash memory holds, it's just a chip, that standard one that's somewhere inside your computer. Usually it's soldered on the main board, and it's stored BIOS or EFI code. Also it's stored ME code, ME partitions. There are actually big region dedicated to management engine, and usually it's not available from operating system. And there is some data related to gigabit Ethernet, and probably there is some other data. And this flash chip controller could operate with DMA, so you could map flash memory to memory of management engine, and also you could use so-called Huffman decompressor. Some data, actually some code models of management engine firmware compressed with Huffman encoding. And there was kind of challenge to decode this data because tables are in hardware and there is no software equivalent that published by Intel. So just to analyze that code, you need to decompress it. Someone did it for older version for management engine, version from 6 to 10, and we and the other guy called Illegal Argument made efforts and discovered tables for management engine 11, and about months ago we published tables for management engine 12 in our account at GitHub. So you could use that code to decompress models, and decompressor is embedded in flash controller. So it's worked directly with management engine without additional efforts. You just tell, please read data from that address to that place in memory with decompression. And also this flash controller could operate in conjunction with HMAX. So data that read, they hash it just during the reading and decompression. Secure key storage is very interesting and very significant part of the security model used by management engine. And there are storage for multiple keys. Some of them 128 bits in length, other for 256 bit in length. And you could put key inside the secure key storage, but you are unable to get it back. But you could use it for cryptographic operations like encryption or HMAC calculation. And very interesting feature that use it in very narrow cases, but it's used inside management engine. It's policies. So you could tell the system that when a key is put on the secure key storage, you could use it, for example, for decryption operation and result could be stored only in secure key storage again. So you could not extract key and you could not extract result of the key usage. But when you perform encryption by advanced encryption standard algorithm on the same key, you could get result in memory. So it's a way they protect data from recovering to memory. So it's like TPM, but for very specific tasks. They protect from attacks when attacker have control inside management engine, because outside of management engine you're just unable to access this device. It's not available to central processor at all. Advanced encryption standard device perform very simple operations. It's perform encryption and decryption. It's have at least 3 modes that supported in hardware: blockchaining modes, electronic code books, cipher blockchaining, and the counter mode. Also, we could put keys inside. Put keys for advanced encryption standard directly or take it from secure key storage, and for sure you could just call DMA initialization, and after that you will be able to decrypt or encrypt data without using of direct commands, just in stream mode. And actually one of ideas what management engine is used for is protection of digital content when you buy it from internet. For example, when you watch video on Netflix, encrypted data passed to memory of your computer, and some encrypted blob with key is passed on your computer. That blob passed inside the management engine. Management engine decrypts that blob with keys that not extractable, and decrypt all the data that make content of the video you're trying to see, and put it directly in video memory of graphics card. So decrypted content just not shown in memory of your computer, so you're unable to steal it. And this is one of goals that could be achieved by using this device. SHA HMAC engine used for calculation hashes, and HMAC based on SHA family hashes. And almost the same, it have different lengths of key for HMAC signature calculation. You could use key directly or from secure key storage, and you could link IS engine with HMAC engine to make encryption with hashing or hashing with decryption in one request very fast. RSA engine is for sure for RSA encryption. We see the code that deals with RSA signature verification in ROM, in some fixed part of management engine that, again, not available to central processor, not changeable by firmware update, but using exploit that was developed by Maxim and Mark, we were able to dump that ROM and analyze its content and figure out how it works. And here is the picture from my presentation from Troopers last year. Here is a generalized picture of layout of secrecy in partition of management engine. When you need to run code from management engine, from Flash, management engine make a lot of verification that code is properly signed. And this part is signed with RSA key, and hash of that key is stored in the ROM. There are 8 such keys, and you need to use the private key, one of that 8 keys, to be able to sign the partition that could hold code that will be loaded and run by management engine. So it's almost impossible to run your own code if you don't have RSA secret key that hold it by Intel or maybe some other parties. So here is the first place where we see RSA engine used. RC4 engine, actually, we were a little bit surprised that we find references to that engine, because this algorithm, it's pretty good algorithm, but it's not considered to be really good right now. And most probably it's used just for backward compatibility with oldest protocols to support, for example, Wi-Fi encryption modes or SSL. And the next important part is security fuses, and now the words to Maxim.
Okay, hello everybody. I will talk about security fuses. Security fuses plays a key role in all cryptography operation in ME. As we will see later, all security key generated on the base of these security fuses. So its value initialized on the some production phase, and this memory is cannot be overwritten, because if you attacker can be read or changing this key, then he can to compromise all platform. And this value unique for each PCI chip. It means that it's a main secret for your platform, and even Intel's engineers can't access to this secret. For example, when he used debugger he can use JTAG for debugging ME, for example. On this slide, you can see how it's implemented in ROM. Fuses available only same short time in the ROM phase. After that, ROM closed access to this memory. And if you platform, if on your platform activated JTAG, for example, vendor JTAG type, it's called orange unlock. You cannot give any information about all keys, but if you have red unlock, it's Intel's unlock. You can read some information for debugging file system, we think. Okay, the fuses we divide into 4 parts because we don't have access to fuses value, but some values can be obtained. For example, we can recovered FTPM, EPIT, and non-Intel key from our platform for our platform, and we can also recover rapid key. We couldn't recover rapid key, but we can use some data which generated on this base for next calculation, and we didn't have rapid SHMA key right on this picture. It is main secret of your platform. If attacker have access to this information, he can generate all keys for your platform. And for example, he can try to execute codes in ME. How this key is used in file system, Dmitry, please tell about it.
So several words about how keys are derived and stored inside management engine. again, last year in December in Black Hat Europe, I made a presentation about security of file systems that use it internally by management engine. And here is a picture from that presentation. And actually, there are up to 10 keys are used to protect secrecy and integrity of data of that's stored on the flash system during runtime of management engine. And there are two sets of key called current keys and previous keys. And the difference is with SVN, secure version number. Intel makes decision that in some situations they need to upgrade version of management engine and prevent rollback to previous version because of serious security issue. And in documentation you could find information that when such situation happens, new firmware will have a bigger version of SVN, security version number, that earlier, but encryption key for file system depends on current security version number, so they need to hold previous version and next version, current version in memory together, just to decrypt old encryption made on old keys and re-encrypt them. So they need to calculate both keys. And inside one version, we have two types of keys for integrity checking and keys for providing secrecy for IS encryption. And both keys could be so-called Intel keys and non-Intel keys. Name of keys, actually, it's our guessing, but Intel engineers, in most cases, just using text string during calculation of keys. They use secret based from fuses and just use it as a key for HMAC and pass the string to HMAC function as a data. So we name keys after that strings. And also two additional keys is for replay protected monotonic counter. It's some feature of SPI flash controller. We never see such controller in the wild. But when controller supports this feature, you will be unable to make rollback of data. So when you write some data, this number is increased, and you cannot write older data without modifying this counter. But when this counter not matches the data that's stored in some special file, system considers that data was broken and stop operation. So these keys are for rollback protection, but in our platform, this feature was implemented in software, and we were able to override it completely because we were able to calculate all the keys that shown on this picture. And here is two slides about calculation of the key. Everything starts from rapid HMAC key. And we use IS decryption using some key. We believe that key is completely filled by zeros, but we are unable to check it because we have no access at that point to the device. So keys are stored in fuses, decrypted and stored in security key storage in slot number 12. Then this key is used to calculate HMAC for two strings. One of them CC wrapping key, and another one CC internal root key plus SVN number. SVN number is just 1 byte number. So we get wrapping key that's stored in slot 21, and then we wrap this data with this key and put it on memory. So this piece just lie in memory between stages of execution of management engine. Here is ROM stages. So another key is calculated from non-Intel root key. And the funny thing that we find that when you're activated JTAG, you're able to read this key. So all secrecy and integrity that based on this key could be broken if you once have ability to run your code on the platform. So algorithm is almost the same. It's again used to calculate HMAC from some string, plus security version number, and this key is wrapped and stored in memory just under other name. And later in BAP stage, BAP, it's a shortcut for bring up. It's a main module that runs on user level of execution. So in management engine, there is like a central processor. There is root, kernel mode, and user mode. And in kernel mode, there is ROM, kernel, and RBE module. And in user mode, there are everything else. And this is first and main module that run in user level. It initializes everything from user stage. And this module just access to the memory stored keys, use key that holds in secure key storage. And one word back, this key will be erased from memory, from secure key storage after ROM finished its work, before it passes control to RBE. So you will use this key because it still resides in secure key storage to unwrap keys, but unwrapped value could not be stored in memory. So this value is used through secure key storage to calculate HMAC for another keys, result for short time stored in memory, and then wrap it with the same key, and after that store it in memory. And this part resides in memory for a long time, and later pass it to VFS module that use it for accessing to file system. It's like a service model for other modules that requires file storage. So you could see that these 4 keys that was shown on these slides, these 4 keys. They are stored in memory in plain text for very short time, just after calculation before they are wrapped. And they, after that, erase it from memory, and you will be unable to find it in memory almost never. So the only way to get this key is just to get code execution ability inside bring up module, because from other modules you will be unable to use hardware security engines. There are only 3 modules that have permission to use IS encryption, SKS, and so on. It's ROM, it's bring up, and crypto module. But crypto module didn't allow you to make some flexible access, and you are limited by using keys that are already available in memory or in secure key storage. So it's kind of paranoid model. A lot of security calculations and the keys are stored in obfuscated form. So I believe it's great idea to make such approach. And now again, word to Maxim.
Okay. We particularly recovered this key. What means particular? We can't get any information about wrapping key from fuses, but we can get a wrapped value and unwrap it on key. Unfortunately, we haven't 18 keys in SKS because ROM deleted it. But we can recalculate its value. After that, we can rewrap key in memory and get information and get value after IS decrypt. Unfortunately, we cannot check. Probably we cannot check. Dmitry said that SKS1 initialize by 0, but we cannot check it because unfortunately we get this information via JTAG, and we think that maybe ME closed access to this value when we JTAG activated, and we couldn't encrypt this value on this key. Okay, the next keys, it's FTPM keys. It generated likely a bit, and we can recover it because we can calculate 18 key, and we can rewrap some data from memory saved in special structure called FTPM keys. This value using in some drivers, some models into ME, for example, TPM module which implemented TPM to 0. And small summary, security keys never holds in memory in plain text, and unusually wrapped key 21 and 18 removed, 21 don't removed and 18 removed from the memory, but all keys we can use for rewrapping data. And almost all key depends on wrapping key, which we cannot know. And how can I say? How I said, even Intel engineer with JTAG are available to get SHMA key because it's main secret of the platform. And now I will start about small magic and funny information about ME. ME has a special partition called IVBP. This system partition for hibernate for warm starting. It's like looks like Hibernate. On this partition, kernel of ME saved information about page structure, about some important data, some kernel important data. And if you can change this partition, you can you have arbitrary code execution into ME on in context of kernel. Unfortunately, for attacker, this partition encrypted and has integrity check by SHMAC, and its partition has special seed which unique for each boot of your system. And of course, it's unique for each PCH platform. How is it key generated? You can use ME using wrapping SHMA key. After that, by SHMA, it used 11 key for SHMAC on data with this string, and SVN. SVN, it's a special field which protect your system against downgrade. And after that, ME calculates this key, and this key using for decryption of IVBP partition and verifying that. Okay. Okay, and Dmitry told about next funny partition.
But also in ROM we find a very interesting code. Actually, ROM trying to find a proper place to start the ME and looks in 3 places. It looks in partition named DLMP, FTPR, and FTUP. I believe that FTUP is upgrade partition, so it's created when you need to upgrade management engine during restart. FTPR, it's normal partition where all code that runs every day is resides. And DLMP, probably D makes debug, probably something other, nobody knows. And in partition DLMP, it looks for module named IDLM. It starts from index 0 and just use index in incremental mode, trying to find the partition. It's check signature according to picture that I showed earlier. And if everything is okay, it's trying to find module with a specific name. And if module is proper one, so it's not modified by attacker or somebody else, it's check if it's have index 0, then this module is executed. So at this stage, you execute code that taken from IDLM module from DLMP partition. If index is more than 0, so management engine ROM locked fuses, so made them unavailable, erase all data that was read from fuses, and derive all keys that necessary for following stages, and execute running module RBE, and ends the execution of the ROM code. And the main idea of this picture that during this stage of execution, system still have fuses in memory. So if you have ability to run code at this place, you're able to execute anything and calculate anything, even things that are not available using JTAG. And here is some info about IDLM partition. Actually, it's the only place where you could put your own code, because you're unable to put your code in ROM. And if you're able to run your code inside IDLM, you have ability to do anything with the platform. You could recover every secret and calculate new values based on the secrets in any future. For SVN, for example, for file system keys, we were able to make code execution on platform with SVN equal to 1. And we are unable to get values for keys with SVN 3 because all calculation of that keys performed in ROM, but we don't have access on ROM. We have ability to trace ROM, but if we'll start in trace mode using JTAG, we have no chance to access to fuses. So it's, again, it's well-designed system, but it's actually decision that allows you to override all other security measures and find everything you need. So final words about our today's presentation. We believe that Intel engineers built really serious and good model to protect secrets within management engine. Even if you have ability to make code execution, you could compromise current platform, current version, but you're unable to extend your knowledge for future version of SVN or for other platforms. And we not sure about content of fuses data. Probably they're just random values because they could be random values, but probably there is some algorithm that use it to generate them for some specific platform, and someone in the world just able to, for example, get serial ID of your motherboard and get all necessary information to calculate all that key. We could not prove or disprove that. But the most interesting thing that we find is that IDLM feature, I'm not sure that it's backdoor. Probably it's kind of ability to make post-ROM decision that actually should be implemented in ROM. So ROM is not modifiable part of the system. Intel never able to upgrade it. For example, Apple was not able to upgrade boot ROM, so all mobile phones prior to iPhone 4 were vulnerable to ROM boot attack for many years because it's impossible to patch. And almost the same here, but Intel still have chance to modify something that was not performed in ROM, like in ROM. But nobody knows what that partition was designed for and who actually owns that keys that use it for signing that partition. And now I believe we spent all our times, and if you have any question, we will answer them. Yeah.
Is SKS vulnerable to side channel attacks? Have you tried that?
We not tried that, and actually it's very hard to try because actually it's a physical device, and you could access it only from management engine, so you could not build every simple device to attacking it and measure time. So it's physical problem to implement it, but probably Maxim have something to that.
Actually, not only SKS used for key storage. For example, you have some device fuses pooler which resend information from some devices to SKS, for example, or maybe ME kernel. For example, many devices integrated into PCH, and it's very difficult to check anything without description on this device. We know about maybe 10 or 11 register of this device, but on bonus slide, after the slide, we have bonus slides. For example, we don't know this, which means this value in IS devices, and
This data is loaded in ROM, but we don't know for what purpose. So we knew that this data is passed inside IS device, but no idea why. And almost code that looks in the same manner, it's again related with IS encryption. This code is taken from crypto module, and again, we don't know what this key means, what it's used for. Probably it's some testing key that just left in code. Probably it's have some special meaning. We don't know. And it's unexplored space. You have chance to do something in this area. I believe that management engine not considered to be like tamper-proof or tamper-resistant device by itself, but it's developed with a very good approach, and just by comparing code that we see inside management engine and inside some other Intel products, it's have pretty good written code. So it have a lot of verification stages almost at every place. It's just we find one place with buffer overflow, and we were lucky to exploit it. But in other places, it's actually very well designed. And paranoid, I call it paranoid key management model. It's not prevents you from physical attacks, but I believe that it's not too easy to get inside the PCH chip, because ME, maybe 10% of that chip, you don't have some special chip that dedicated to management engine. You need to get inside bigger device, and it's very hard. So I think that physical attack on such devices will cost maybe hundreds of thousands of dollars. If there is no more questions, thanks for attending.
thank you for your attention.